Okay, children, now we'll study about elastic constants. So, what are the different elastic constants? Modulus of elasticity we have studied. It is represented by the letter capital E, that is equal to sigma linear stress or normal stress by E. Second moduli of elasticity is modulus of rigidity. It can be represented by the letter capital G or capital N. It is equal to shear stress Q by shear strain phi. Now what is bulk modulus? Bulk modulus K is equal to volumetric stress by volumetric strain. So we can represent it by the letter P. What is P? P is the identical pressure in three mutually perpendicular directions. So if you have a parallel pipe like this, which is subjected to equal pressures on all the sides. So when a body is subjected to identical pressures P in three mutually perpendicular directions, the body undergoes uniform changes in three directions without undergoing distortion of shape. So bulk modulus is the ratio of change in volume to original volume is defined as volume strain or volumetric strain. So the bulk modulus K can be written as K is equal to identical pressure in three mutually perpendicular directions divided by volumetric strain. Now you know what is volumetric strain. It is change in volume by original volume. Okay. So how can you define bulk modulus? As a ratio of identical pressure P acting in three mutually perpendicular directions to the corresponding volumetric strain. So here this figure shows a body subjected to identical compressive pressures P in three mutually perpendicular directions along X, Y and Z. Since hydrostatic pressure, the pressure exerted by a liquid on a body within it, has this nature of stress, such a pressure is called as hydrostatic pressure. Okay. Okay, now we'll find out the relationship between modulus of elasticity and bulk modulus. So you consider a cubic element subjected to stresses sigma in three mutually perpendicular directions x, y and z direction sigma. Stress sigma in x direction causes tensile strain sigma by E in x direction, while the stress sigma in y and z direction causes compressive strain along the x direction. So how can you write Ex? That is the strain in x direction sigma by E in the x direction, which will cause increment in length, that is tensile strain, increase in length. Now mu is equal to Ey by Ex. So what is Ey? Minus mu into Ex, because the strain in the stress in the x direction causes negative strain in the y direction, and that is compressive strain, and also strain in x direction causes compressive strain in the z direction also. So when we are applying sigma in the x direction, there will be elongation in the x direction and compressive strain or decrease in length along the y direction and the z direction. So we can write Ex, that is the strain in x direction, is sigma by E, which is positive, minus mu into sigma by E, which is the strain caused by the stress in the y direction. Strain in x direction due to stress in y direction is minus mu into sigma by E, and strain in x direction due to stress in z direction equal to minus mu into sigma by E. So you can write sigma equal to 1 minus 2 mu. Since all these perpendicular directions are subjected to same stress, you can write the equation for strain in y direction as sigma by E into 1 minus 2 mu, and strain in z direction is sigma by E into 1 minus 2 mu. Now we have to find out what is the volumetric strain. So here we can write volumetric strain is equal to strain in the three mutually perpendicular directions. Volumetric strain we are representing by the letter small e suffix v, and this is equal to Ex plus Ey plus Ez. So substituting these values, you will get 3 sigma by E into 1 minus 2 mu, because Ex equal to Ey equal to Ez equal to sigma by E into 1 minus 2 mu. Now what is bulk modulus? You know, bulk modulus is equal to, it is represented by the letter capital K, and this is equal to stress, equal stress in three mutually perpendicular directions divided by volumetric strain. So this is equal to sigma divided by 3 sigma E into 1 minus 2 mu. So this will be reduced to E is equal to, from this you can write E is equal to 3 into K into 1 minus 2 mu. Okay. So this is the relationship between modulus of elasticity and bulk modulus. You have to by heart this equation. Okay, now we have to find out the relationship between bulk modulus of elasticity and modulus of rigidity. For this, you consider a square element A, B, C, D. So written in black ink, A, B, C, D, of sides A subjected to a pure shear Q as shown in figure. Now A, E, C dash, D shown is the deformed shape due to shear small q. So this is the deformed shape due to shear small q. Okay. Now you drop a perpendicular BF. Drop a perpendicular BF to diagonal DE. DE is the diagonal of the deformed shape. Drop a perpendicular BF to the diagonal DE. Let phi be the shear strain and G is the modulus of rigidity. So consider a square element ABCD is subjected to pure shear. Now A, E, C dash, D is the deformed shape. Now we have to find out what is the strain in this, shear strain in this diagonal. For that you drop a perpendicular BF to the diagonal DE. So what is the angle between the shearing plane and the diagonal? This is the shearing plane. Angle between the diagonal and shearing plane is 45 degree. Now we are assuming that the shear strain is very small, phi is very small. So the deformation is very small, and hence this angle remains the constant. That is the angle between the shearing plane and the diagonal DE remains constant. It will not change. That is, this angle will also be equal to 45 degrees. So our assumption is this angle is equal to 45 degree. Okay. So we have dropped a perpendicular BF to this deformed diagonal. Let phi be the shear strain and capital G is the modulus of rigidity. Okay. Now we have to find out what is the strain in diagonal BD. So we have to find out what is the strain in the diagonal DE. So DE, we have to find out what is the change in length. Final length is DE. Now the initial length was BD, but it is approximately equal to FD because the deformation is very small. DE minus DF divided by original length, that is DF. So what is DE minus DF? This is DE, final length. Original length is DF. We are taking it DF is equal to BD, because we have dropped a perpendicular here. So DE minus DF, it is the change in length. By original length is DF. Okay. Now what is this DF? DF is actually equal to DB. So we can substitute here. This is equal to DE DE minus DF. What is DE minus DF? This is DE. DE minus DF is EF. EF divided by DF is actually equal to DB, the length of the diagonal. This is equal to EF divided by, here it is given A is the side of the square. So diagonal is root 2 into A. Now since this angle of deformation phi is very small, we can take this angle is equal to 45 degree. That is the original angle of the diagonal made by this shearing plane is 45 degree. So this angle will also be equal to 45 degree. Okay, so we can assume angle BEF equal to 45 degree. So from this triangle, what is cos 45? Cos, this angle is 45 degree. Actually this angle is 45 degree. So what is cos 45? Cos 45 equal to EF divided by BE. So we can write EF is equal to BE cos 45. BE cos 45 divided by root 2A. Now here from this figure you can write this angle is equal to phi. That is the shear strain. So we can write from this triangle tan phi is equal to BE divided by A, because this side is A, opposite side by adjacent side. So we can write BE is equal to A tan phi. So you can substitute here A tan phi into 1 by root 2 divided by root 2 into A. So this is equal to 1 by 2 tan phi. For very small angles we can take tan phi equal to phi. So this becomes phi by 2. So now you have got the relation strain in diagonal BD equal to phi by 2. So what is phi? Phi is shear strain. So you can substitute phi is equal to Q by G. So you will get the strain as 1 by 2 into small q by G. We have seen that this square element is subjected to pure shear. This pure shear give rise to axial stress, tensile stress Q in the diagonal direction of dB, and axial compression at right angle to it. So these two stresses causes tensile strain along the diagonal dB. Okay, this Q causes tensile strain. Since this is compressive along AC, it will cause tension in BD. Okay, since the two stresses, this Q along the diagonal BD and this Q along AC causes tensile strain, we can write Q by E, strain in BD due to this Q along BD is Q by E, and the strain in that diagonal due to this Q acting along AC, diagonal AC, equal to mu into Q by E. This is positive because it is causing tensile strain. So you will get Q by E into 1 plus mu. Now equating equations 1 and 2, you can write here 1 by 2 into Q by G is equal to Q by E into 1 plus mu. So you will get the relation capital E equal to 2G into 1 plus mu. So this is the relationship between E and G. So you have to by heart this equation. Okay. So you have got the relationship between E and G and E and K. So we can establish a relation between E, G and K. E equal to 2G into 1 plus mu. From this you write mu equal to E by 2G minus 1. So you will get the relationship E equal to 9kg by G plus 3k. Okay. Thank you.